Let us start lecture 39. The course is on phase diagrams in single component and binary systems. And today we will continue our topic what we had started last lecture, that is isomorphous phase diagram. In fact, if you go back and see the last lecture, you would see that we have actually taken the information from free energy composition plot for a binary system with liquid and solid solutions to a plot which actually reflects the plot between temperature and composition at a constant pressure, and we have kept the pressure as at 1 atmosphere. So, we could do for 4 temperatures. So, one temperature was chosen in such a fashion, that is, it is in complete liquid zone. Another temperature was chosen which was in complete solid zone, and 2 other temperatures which were equal to the temperatures or the melting temperatures of those pure components A and B. So, now we have to do another free energy composition plot which will reflect the equilibrium between 2 phases, that is solid and liquid solutions, when the temperature is chosen between the 2 melting temperatures. One is melting temperature of B, another one is melting temperature of A. And also at the same time we have to see how that equilibrium is reflected on temperature composition plot. So, then we will see the complete plot starting from complete liquid zone to complete solid zone, and that plot how it comes up we will see that today. So, the today's topic is isomorphous phase diagram, and if you recall couple of things we will just reflect. So, then you would understand that what we are planning to do today. So, here what we are doing, we are taking ideal solution, ideal solid and liquid binary which is A and B. These are 2 metals, binary solutions, and every time we will be taking 1 mole of solution, 1 mole of solution. So, hence, and that means XA, which is the mole fraction of A, and XB, which is the mole fraction of B in the solution, when they are added up it should lead to 1. We will keep temperature and pressure constant. In fact, pressure is 1 atmosphere, and at different temperatures we have to do the composition, free energy composition diagram for both the solutions, and then we have to reflect that information, equilibrium information on temperature composition plot. And another information is TMA, melting point of A is less than TMB, and we have done for 4 temperatures, which was at T1 which is less than TMA, then another temperature we have chosen which is T3 which is greater than TMB, and we will be doing one more temperature which is T2 which is in between TMA and TMB. And if we look at the information on temperature composition plot, so this is temperature, this is XB, and this is pure B, this is pure A. So, that means XA equal to 1, this is XB equal to 1, and we have seen that this was one temperature, this was one temperature which is T3, then another temperature was TMB, and here one temperature was T1, this is another temperature which is TMA, fine. And we have seen that at T1 solid solution is stable at all compositions, but at Tm at Xa equal to 1, solid and liquid will coexist, solid and liquid solution. Tmb, solid and liquid solution again will coexist, and at T3 we will have all liquid. So, here all liquid, here all solid, and at this location solid and liquid solution of pure A will coexist, pure A, and here we have solid and liquid of pure B will coexist. Okay. So, now we will be seeing at this temperature what happens. This is T2. Now, we have to also consider the standard reference value, and for that we have to also see how the plot of G versus T for pure metals A and B look like. G and this is T, and one case was this was G B naught for solid, this is G naught B for liquid, and this corresponds to Tm B, okay, melting point of B. The another one was this is G naught A solid, this is G naught A liquid, and this particular point corresponds to Tma, and 5 temperatures are like this. One was here, which is T1, another one was at Tm, this is another temperature. So, we are choosing T2 here, T3, the another temperature which was chosen is this, and then we have also seen for T3. So, now our interest is at T2. Now, at T2, let us take the reference point. At T2, we see that for A, G A naught liquid is less than G naught A for solid. So, that makes me to assign 0 value to liquid, pure A liquid. So, this is, that means G A naught liquid should be considered as 0, and whereas for B, G naught B solid is less than G naught B liquid. So, that way I can assign solid to be 0. And remember, we are putting all case this naught, that means it is a standard pure condition at 1 atmosphere, and temperature can be any temperature over this entire G versus temperature plot. Now, once we consider that, let us draw free energy composition plot. See, if I draw free energy composition plot, let me plot it here. So, let me just check what color we have considered. The green color was chosen for solid solution, and then violet color was chosen for liquid solution. We can do the same way. So, I can take green for, so first let us assign those values. This is my G versus, this is G, this is XB, pure A, and at this point it is 0, this is 0, this is pure B side. Now, here I have to take G A naught L, and this side G naught B solid. Now, accordingly I have to place G A naught solid and G B naught liquid. So, G B naught liquid is placed here as per this particular G versus temperature plot. This is G B naught liquid, and here it said, let us say this is considered as A naught solid. Okay, fine. So, once we have assigned them, now I can decide what would be my G1 for solid and liquid before mixing. So, this would be my G1 for liquid, and another one was this is G1 of solid, or let me just put it in the bracket. Now, solid free energy G2 line would then be, and remember at that temperature, if I try to consider delta G mix, that will be same for liquid solution as well as solid solution value wise, because if I try to look at G2, G1 plus delta G mix, and delta G mix equal to RT XA ln XA plus XB ln XB. Okay, fine. So, that will be same contribution towards the solid solution as well as liquid solution, which is G, solid or liquid, and this would be same for solid and liquid. So, if that is same, then I can have equal contribution. So, this would be like this, and the another one was this was the liquid solution. Okay. This is G2 solid or G2 solid, and this is G2 liquid. Okay. So, now we have to find out the equilibrium between those two phases. We have already understood that the common tangent would allow us to find equilibrium of two phases in a system, and that would also tell me what are those two unique compositions those are in equilibrium. So, that common tangent needs to be drawn, and so if I draw that common tangent, so common tangent will pass through like this. Okay. This is the common tangent, and if I extend it, you will see that here G A bar L equal to G A bar solid, and here G B bar liquid equal to G B bar solid. So, chemical potentials of both the components in solid as well as liquid solutions are equal. So, that suggests equilibrium at that temperature. So, this is at T2, pressure is always 1 atmosphere. So, now we see, so this particular point and this particular point, these 2 points are under equilibrium. So, this is the composition. Let us say this composition is C solid and this is C liquid, and remember this is with reference to B. So, these both the compositions are with reference to B. So, that means those are actually XP. Now, I have to just put these 2 points over the T2 line on T versus XP. So, those 2 points if I try to look at, so one point would appear here and another point would appear here. So, this is C solid and this is. So, there was a small corrections, please do that correction. I think we wrongly reflected these 2 lines, because liquid line G1 should correspond to G2 for liquid. So, let me just change the color. Okay. So, this color would be, please change that corrections. this would be this, and then green one would fall on, this would be for, please make these corrections. Okay. So, this is for, okay. So, that correction please incorporate. So, this would be solid, this would be for solid, and this would be for liquid, and this is G2 liquid, and this is G2 solid. So, we are correcting the mistake because G1 line, this is the G1 line. So, that G1 line should have a correspondence to a liquid solute solution, a liquid solution, that is G2L, and G1 solid would corresponding to solid solution G2S. So, that is a small corrections. So, here it would be now, and rest of the things would remain same. The common tangent, and these are the 2 points where the equilibriums are established between two solutions, solid as well as liquid solutions, and these are the 2 points, this point and another point is this, these 2 compositions only will be under equilibrium, okay, and these 2 compositions are with reference to B. So, this particular composition, just take it to the temperature composition plot, and that only thing is these 2 compositions will be exactly falling on this T versus XP plot. So, this will be for liquid and this would be for solid. Like that way, if we keep changing that temperature, whether I will shift this way or this way, I would have a situation like this point. If we go up with this temperature, this point, let us say I reach to another temperature here. This is another temperature. You will see that liquid point would shift here, solid point would shift here, okay. Like that way the shift would happen. So, this will be all liquid point and this will be solid point. And similarly, if I go below this T2 temperature, but still I am keeping the temperature between 2 melting points. So, there I will see that the solid liquid point would shift here and the solid point would shift here, like that. Okay. So, let us say if I reflect the liquid point on a different notation. So, I will put a like this and the solid point only the arrowhead. So, now if I connect those liquid points and solid points at different temperatures, if I connect that, I will get a plot like this. So, I will just connect them, okay, and the liquid solid line if I connect, I will get like this, okay, fine. I see that it actually gives me a kind of I-shaped pattern, okay, and where this line reflect liquid and this line reflect for solid, fine. And how it happens? Let us take a diagram at a take this particular diagram at a temperature little higher than T1, but still in between TMA and TMB. If I take it at a higher temperature, this is 0, pure B, pure A, and this is G A naught liquid and this is G A naught solid, and T at let us say T prime, which is little more than T2, but still it is in between 2 melting points. Okay. So, that case, so it will fall little below, this is G B naught liquid and this will go up little bit. Solid. this will go a little up. Why? If you try to look at a temperature T prime, this is my T prime, okay. So, you see that the gap between solid A and liquid line is increasing, whereas at T prime the gap between solid and liquid line for B is actually decreasing. So, that is what decreases and this gap increases compared to this one. Okay. So, now if I try to look at G1, so this would be my G1 liquid and the another one was the solid line G1 solid. So, now solid one should be plotted like this, it will in fact it will further go down at a higher temperature. It will further go down. Why? Because at a higher temperature minus T del S mix, since temperature is increasing, del S mix would not change, that expression suggests. So, with increasing temperature this quantity will go further down in that del S further down in this plot. So, that is what this one will also go down. Okay. Now, similarly on the other side, if I try to look at G1L, that would be, and here you see here the gap is decreasing. So, this gap has decreased. So, that means it will be further down. Okay. So, like this. Now, if I try to do the common tangent, so this will be common tangent, this will be common tangent. Here G B bar liquid equal to G B bar solid, and in this case G A bar liquid equal to G A bar solid. So, that those two compositions will be under equilibrium, and this is G2, this is G2 liquid and this one is G2 solid. This composition is C for solid and this composition is C for the composition XP of liquid. Okay. And since it is prime, so let me do it with a prime sign. Now, if we try to compare with this curve which is at T2, this is at T2 and this is at T prime, and since T prime is greater than T2, so this particular composition has shifted compared to this composition and this one also has shifted compared to this composition, and every shift is basically towards the right. So, now if I try to reflect these two equilibrium points on T versus composition plot, and these are the 2 points. Okay. These are shifted, these are not with the scale. If you perform it with the calculation, you will see that that will come with the scale also, and that will show also with the equation that how to draw this particular diagram. So, now these are the two compositions. Now, this is for solid composition and this is for liquid compositions at T prime. So, this is at T prime. Similarly, you will see that at T double prime, which is less than T2, but in between melting point of A and B, if I consider this one which is T double prime, you will see that diagram would move in such a fashion that this one was, this Cl will shift left and Cs also will shift at T double prime, because that T double prime is less than T2, but in between two melting points. So, that equilibrium compositions of solid solution and liquid solution will switch towards left, and that is what I have shown, that these two lines, these 2 points have shifted to left to compare to these two compositions. Fine. So, accordingly we are actually connecting those equilibrium points at different temperatures, and we are seeing isopid plot like this. This typical plot is called isomorphous. Isomorphous diagram, phase diagram. So, if I try to plot separately, and this diagram is coming from the composition, free energy composition plot at different temperatures, and for that we need information of G versus T for pure metals, assigning the reference values to different pure metals rather at in of solid as well as liquid, and accordingly we see the equilibrium compositions and plot it here over T versus XP, and that gives me an isomorphous phase diagram. And here remember, over the entire composition range we have complete solubility, okay, whether it is in liquid or solid. And if I try to show this plot, that plot is like this. This is X A equal to 1 pure A, this is X B equal to 1 and X P is changing this way, this is temperature and this is X P, and the plot was like this, and here everything was liquid, here everything was solid. At this point we get Tm A, at this point it is Tm B, and in between, let us look at in between what happens. In between, if you see that if I try to look at T2, two compositions are in equilibrium, one is for liquid solution, one is for solid solution, and whatever composition you take in between. So, if I take let us say this composition or this composition or this composition, any compositions you take in between this two composition range, initially to start with, you will always see that composition will divide into two parts, one is Cl, another one is Cs, and only those two compositions will be existing. And what are the two phases? Because since those two compositions are for the two phases only, those are in equilibrium. So, one is solid, one is liquid, and both are in solution stage. So, that means in between we will have solid solution plus liquid solution, and if I try to look at any temperature in between TMB and TMA, so let us say these are the two temperatures, this composition will be for liquid phase and this is for solid phase of composition Cs and this is composition Cl. So, in between these two compositions, all the thing will convert, any composition you take, all the thing will convert into these two specific composition of solid and liquid. Okay. So, and any temperature you take it, you take any temperature, you will see, even if you take this point, this is also solid and liquid, this is also solid and liquid. Of course, this is pure A and this is pure B at extreme points of X A equal to 1 and X A equal to X B equal to 1. So, this is pure B. All these two extreme points also is actually segregating into two phases, solid and liquid. At extreme point it is of the same composition, but in between that I, any composition is divided into two compositions because those two compositions are in equilibrium. Okay. So, that is why in between that I, solid and liquid phase will coexist of two different compositions, those are in equilibrium as per the free energy composition common tangent rule, and above the top line everything would be liquid solution, below everything would be solid solution, no compositional differences, all the compositions will be solid. Okay. And above that, so that is what this particular line we call it liquidus and this line we call it solidus. Okay. So, these are the informations we can get out of it. fine. In fact, we can also get one more information, that is called the fraction of solid and liquid phase in the I zone. Okay. So, that we will do it in the next lecture, as well as we will try to also find out equations considering ideal solute solution as well as liquid solution approach, and then by solving that equation we can get such phase diagrams. So, this is called isomorphous phase diagram. Fine. So, we will continue our discussion on this isomorphous phase diagram. We will try to find out the fraction of phases if I take a composition and temperature which will be falling within that I zone. Okay. So, till then, thank you very much.